Two algorithms walk into technical interview. Both claim they split a problem into smaller subproblems. Both recurse. Both look nearly identical on a whiteboard. But one runs in O of n log n and the other explodes to O of 2 to the n. The difference is not in how they divide the problem. It is in whether those subproblems ever meet again. Today we are going to make that distinction permanent in your memory. Divide and conquer versus dynamic programming. Same high-level skeleton, completely opposite runtime fates. We will build the intuition from first principles, walk through the canonical visualization, and end with a decision framework you can apply in any interview or production codebase. Here is the question that trips up almost every developer the first time they encounter it. Both strategies split a problem into smaller pieces and recurse on each piece. Why does one blow up exponentially while the other stays polynomial? The answer comes down to one word: overlap. Divide and conquer assumes its subproblems are completely independent of each other. When merge sort splits an array in half, the left half never needs any information from the right half to sort itself. They share zero work. Dynamic programming is designed for the exact opposite situation. When you call fib of 5, you need fib of 4 and fib of 3. Fib of 4 needs fib of 3 and fib of 2. Fib of 3 gets computed multiple times across the tree. That redundancy is the enemy, and DP eliminates it by caching every result the first time it is computed. Draw the recursion tree for fib of 4 using naive recursion. The root node calls fib of 3 and fib of 2. Fib of 3 calls fib of 2 and fib of 1. Fib of 2 now appears in 3 separate branches of the same tree. Fib of 1 appears in 2 places. Every node highlighted in red is a subproblem being fully recomputed from scratch, throwing away work that was already done. That duplication compounds exponentially, giving a tree with O of 2 to the n nodes for an input of size n. Dynamic programming sees the same recursion tree but adds one crucial layer: a cache. The very first time fib of 2 is computed, its result is stored. Every subsequent call is an O of 1 lookup. The entire exponential tree collapses to a single linear chain of n unique computations. Same recurrence relation, completely different runtime because of that one design choice. So how do you decide which strategy to apply? Start with a single diagnostic question: do any subproblems overlap? If the same subproblem appears more than once anywhere in your recursion tree, you are firmly in dynamic programming territory. If every subproblem is unique and independent of the others, divide and conquer is the right tool. Then, if you are on the DP path, ask a second question: does optimal substructure hold? That means the optimal solution to the whole problem can be constructed from the optimal solutions to its subproblems. If optimal substructure holds, DP gives you a provably optimal result. If it does not hold, you may need a greedy algorithm or a completely different approach. This two-question decision flow handles the vast majority of algorithm design choices you will encounter in competitive programming and real production work. First dynamic programming technique is memoization, also called top-down DP. You write the natural recursion exactly as you would in a naive implementation, but you add one critical step: before computing anything, you check a cache. If the answer is already stored, return it immediately in O of 1. If it is not stored, compute it recursively, store the result in the cache, and then return it. The outcome is that each unique subproblem gets solved exactly once, no matter how many times it appears in the recursion tree. For Fibonacci, this transforms 2 to the n recursive calls into just n unique calls. Looking at the call trace, fib of 2, fib of 1, and fib of 0 are all computed on the first descent, and every single subsequent reference to any of those values is an instant cache hit. Time complexity drops to O of n. Space is O of n for the cache plus O of n stack depth. The second technique is tabulation, also known as bottom-up dynamic programming. Instead of recursing downward and caching on the way back up, you build a table starting from the smallest known base cases and fill it incrementally in the forward direction. No recursion at all, no call stack, no risk of stack overflow on inputs with large n. For Fibonacci, you initialize dp bracket 0 to 0 and dp bracket 1 to 1, then run a simple loop from 2 to n, filling each cell from the 2 cells before it. The recurrence dp of I equals dp of I minus 1 plus dp of I minus 2 is made concrete as a table entry. You can even eliminate the full table entirely and keep only 2 rolling scalar variables, reducing space from O of n down to O of 1. Bottom-up is typically faster in practice because of better CPU cache locality and the complete absence of function call overhead. Putting both strategies side by side with concrete complexity numbers reveals the full picture. Merge sort uses divide and conquer. Its recurrence T of n equals 2T of n over 2 plus O of n resolves via the master theorem to O of n log n time with O of n space. Binary search gives T of n equals T of n over 2 plus O of 1, collapsing to O of log n, elegant and optimal. Now look at naive Fibonacci without any caching. T of n equals T of n minus 1 plus T of n minus 2, which grows as theta of the golden ratio to the n, approximately O of 2 to the n catastrophic for any meaningful input. Add memoization and it immediately collapses to O of n time. Edit distance and longest common subsequence both run in O of m times n time and space. 01 knapsack runs in O of n times W. All of these trade space for a massive time saving over exponential brute force. Recognizing which type of problem you're facing before writing any code is a critical skill. Watch for DP signal words in the problem statement. Optimal, maximum, minimum, count the number of ways, shortest path, longest sequence. If a problem asks you to optimize or count something across a sequence, a grid, or a set of binary choices, dynamic programming is almost certainly the right tool. Contrast that with the divide and conquer signals. Sort these elements, search this data structure, have the search space, split and conquer. If the problem naturally breaks into two equal, fully independent halves that can be solved separately and then combined, reach for D and C first. The clearest practical test for DP is simply to sketch the recursion tree for a small input and check whether the same subproblem node appears in more than one branch. If it does, you need memoization or tabulation. Trade-offs between these two strategies extend beyond raw asymptotic complexity. On memory usage, divide and conquer typically needs only O of log n stack space because its independent subproblems require no persistent cache. Dynamic programming requires O of n or O of n squared for the memo table, which becomes a serious constraint when the input size or the weight parameter in a knapsack problem is very large. On parallelism, divide and conquer is embarrassingly parallel. Merge sort can process the left and right halves simultaneously on separate cores with zero coordination overhead. DP tables have strict data dependencies where each cell must wait for previously computed cells, making parallelism significantly harder to achieve without specialized wavefront scheduling techniques. The most common D and C mistake is applying it naively to a problem that actually has overlapping subproblems, producing exponential runtime. The most common DP mistake is allocating a table so large in both dimensions that it exhausts available memory. Always verify your subproblem structure before committing to either approach. These are not abstract academic exercises, they are the implementation choices behind tools you use every day. It uses the Myers diff algorithm, which combines a divide and conquer decomposition with a DP edit distance core to compute the minimal edit script between two files. Every time you run git diff, you are watching both strategies cooperate. Operating system schedulers use hierarchical divide and conquer partitioning to assign processes and threads to CPU cores. Language model inference uses the Viterbi algorithm, which is DP over a sequence of token probability states, running in O of vocabulary size times sequence length. The Bellman-Ford shortest path algorithm, which powers BGP routing across the internet backbone, is simply DP edge relaxation repeated v-1 times across the entire graph. Once you internalize these patterns, you start seeing both strategies everywhere in the systems you build and depend on daily. Here's the mental model to carry forward from this video. Both strategies divide a problem into subproblems and recurse on each one. The single question that permanently separates them is this: does your recursion tree contain the same subproblem in more than one branch? If yes, that repeated work is waste, cache the result, and you have dynamic programming. If every branch leads to completely unique subproblem, recurse freely without any cache, and you have divide and conquer. That one diagnostic question correctly classifies the overwhelming majority of algorithm problems you will ever face. Internalize it, apply it before writing a single line of code, and watch your interview performance and system design instincts sharpen immediately. Thanks for watching.